be simulated in a room, we represent it using what we call the plane of density function A, which is also a function of frequency and direction, and it encodes the directionality of the sound field. And so if we want to have this virtual listener inside this room, we need that the HRTF and the point that we're measuring the sound field will be aligned, so with the same coordinate system. This is important to note here. So if we have these two functions, we can reproduce the binaural signal simply in space domain using integration, or alternatively in the spherical harmonics domain using the spherical harmonics coefficients of the sound field and the HRTF, which is beneficial for many reasons. One of them that in the sound field, these are the known ambisonic signals, and also in the HRTFs, it's beneficial to represent it in the spherical harmonics domain. But the problem is that practically we can't really sum up to infinity, and we have only, we can reproduce the binaural signal only up order n, which is determined by the minimum order between the sound field and the HRTF we have. And the problem is that typically we are limited by the order that we can get, or if it's coming from microphone array recordings, or even from simulations, for other reasons. And the HRTF is known to be of high spherical harmonics order. So this causes truncation error that affect directly the spatial perception. It's been shown to reduce the spatial resolution. It causes spatial artifacts, and also loss of energy at high frequency. So the first question is, how can we reduce the order of the HRTF without losing information? So there are different methods that we're trying to do this. What we're using here is what we published last year in IEEE, HRTF with ear alignment. So I'll explain shortly about this method and how and why it's important to us. So the idea is that we can reprocess HRTF, and by this reducing its effective spherical harmonics order. So we showed that instead of having the HRTF defined around the center of the head, if we are aligning it to the ear position, we are reducing the dimensionality significantly. And this can be done analytically for any given measured HRTF. We can compute the ear-aligned HRTF by this simple phase correction that depend on only two parameters, the radius of the head and the relative direction between the sound source and the ear. And this process is invertible, and the phase information is preserved. So just to demonstrate the dimensionality reduction using this method, so here what we see is the spherical harmonics energy at each order n as a function of the order n and frequency. Black mean higher energy and white mean lower energy. And we see this two different lines here, the green one and the red, represent at each frequency what is the required order preserved 90% or 99% of the energy. So with the unprocessed HRTF, the left plot here, we can see high energy at high frequencies and high orders. And with the ear-aligned HRTF, we see that the energy is reduced significantly at high orders. And for example, looking at 15 kilohertz, for preserving 90% of the energy, the unprocessed HRTF, we need order 21, and with the ear-aligned HRTF at high orders. And for example, looking at performing some manipulation on the linear phase of the HRTF, which is exactly what we're doing here. So we decided to use this method because we showed that it produced similar result to the best method, and it's more robust because it's done parametrically. So now the question is, how can we use such HRTF and convolve it with the sound field while preserving the phase information? So going back to the system that I showed before, now if we have HRTF that is, instead of find out the center of the head, we have two different positions to the HRTFs in the left and right ear. So now the question is what we can do with the sound. And this is what we call the bilateral ambisonics reproduction. So the aim is to incorporate the pre-processed HRTF into the binaural reproduction process. So to remind, the standard ambisonics reproductions, as we see here, is the binaural signal computed using ambisonic signals computed at the center of the, relative to the center of the head, and Spherical-Harmonics coefficient of the HRTF for the left and right ear, relative to the same coordinate system. What we are suggesting is to compute the bilateral ambisonics, which mean two different coordinate systems for the left and right ears, and then we can incorporate the ear-aligned HRTF, but we need two different ambisonic signals for the left ear and for the right ear. So to show the performance of this method, we did an objective analysis by looking at the normalized mean square error, so the error between a reference signal and the evaluated signal. So what we see here is what is the required order to get a certain mean square error, normalized mean square error of minus 20 dB in green, minus 15 dB in blue, and minus 10 dB in red. As function of frequency, the solid lines represent the standard reproduction, and the dashed line represent the bilateral reproduction. So we clearly see how we need much less orders with a bilateral reproduction, especially at high frequencies. And for example, at around 5 kilohertz, to get an error of minus 10 dB with a standard reproduction, we need order 8, which corresponds to 81 Spherical-Harmonics coefficients. And with the bilateral ambisonics, we need only order 2, which means 18 Spherical-Harmonics coefficients because we need two different ambisonic signals for the left and right ear. So it's 9, it's twice 9 coefficient. To evaluate this subjectively, we did perform the Mehra listening test. So we used a simulated sound source in a room, a quite reverberant room of around 1 second reverberation time. This is a room, it's quite big room. The listener is in red here, and the sound source is a blue. So the listener and the same height, and the source is 30 degrees to the left of the listener. For the HRTF, we used the Newman K100 HRTF. It's a measured HRTF around this mannequin head. As a reference signal, we use the standard ambisonics with a high order n equals 41. And for test signals, we have the standard and bilateral ambisonics reproductions of order 1, 2, and 6. So in total, at each Mehra screen, we have 7 different signals, 6 test signals, and 1 hidden reference. And we have 3 screens for 3 audio source signals, castanets, guitar, and speech signal. So we have results of 15 experienced subjects. Experience, I mean that they listened before to spatial sound and performed similar experiment before. So these are the Mehra results. So what we see, the y-axis is the Mehra score, where subjects were asked to rate each signal relative to the reference, how different it compared to the reference. Where 100 mean no difference and 0 mean big difference between the reference and the test signal. And by difference, we instruct the subject to evaluate all the possible differences, so both spatial and temporal and also temporal differences. So overall different. So the three first signals here are with standard reproductions of order 1, 2, and 6. And we also applied equalization, tapering equalization, and spherical head equalization that suggested to improve the low order standard reproduction. Here we have the three other signals with the bilateral reproduction and with the same orders 1, 2, and 6. And we also have the results of the hidden reference. So we clearly see the advantage of using bilateral reproduction, especially compared to order 1 and 2 with the standard reproduction. The results are really low. And interesting to see here that first order bilateral reproduction performed as good and even better compared to sixth order with standard reproduction. And going to order 2 and above, the result is really similar to the reference. Similar trends we can see with the other source signals. So this is for the speech. Although, yeah, all the results are higher because the speech signals contains less energy at high frequencies, and also the castanet signal is much more with much more temporal complexity to it. But still, we see similar trend. Order 1 with the bilateral is comparable to order 6 with standard, and again, order 2 and above is really similar to reference, and similarly with the guitar signal. So we can summarize that order 1 bilateral ambisonics proposed method with only 8 Spherical-Harmonics coefficients, we get similar performance and even better than using 49 Spherical-Harmonics coefficients with the standard reproduction. And using order 2, it's already similar to high order reference signal. So to summarize the method, so this is the standard ambisonics reproduction. We have Spherical-Harmonics coefficient of the HRTF and of the ambisonic signal of the sound field. We can perform the binaural reproduction in the Spherical-Harmonics domain. And we are suggesting to use the ear-aligned HRTF. So we have the two different coordinate systems for the left and right ear. And similarly for the sound field, where we can, for example, measure it using this first order microphone. So two first order microphone can reproduce two different binaural signal, ambisonic signal. And then we can compute the bilateral ambisonics reproductions separately for the left and right ear. So this is the overall process. So it was shown to substantially reduce the required Spherical-Harmonics coefficient, so more than 80% reduction. Preserve the phase information of both the HRTF and the sound field. So we are not assuming anything about the HRTF, not minimum phase or anything like this. But it requires the sound field to represent in the 2 years location. So for example, we can measure it using the sound field, two sound field mic. But then, for example, one limitation is incorporating head rotation. So instead of a simple relative to the center of the head, now we need to do 6 degrees of freedom rotation and translation of the sound field. So this is one limitation of this method. But practically, this can be used for a virtual sound simulation, for example, when we required much less Spherical-Harmonics coefficients, but we need to simulate the sound field at 2 points. So we have some cost to this. We can also use it practically by using 2 sound field microphone recordings, as I said before, plus HRTF. We can get high quality binaural sound, as I showed, comparable to 6 order with standard reproduction. And this is done with only 8-channel microphone. But for example, the head tracking is not revealed using this method. Although here, for example, we can use what was presented yesterday about applying head tracking to binaural signals directly. So there are solutions for this. Another practical use is to improve spatial sound from standard ambisonics. So for example, if we have already simulated or measured ambisonic signals using a microphone array, if we can know how to if we know how to derive the bilateral ambisonics from the standard ambisonics, we can improve the spatial sound, but it requires additional research. The next step, the first one, will be to find a way to compute the bilateral ambisonics from standard ambisonics, to incorporate head tracking, and of course to do more perceptual evaluations, because we only did a simple Mehra test with one static source in a simulated room, and to compare the performance with the previous suggested method, like the frequency-dependent time alignment method that was recently suggested. So yeah, thank you very much for listening. Be happy to take your questions. Thanks. Yeah, it was quite fast. I hope that I didn't talk too fast.
Len, go ahead and ask your question.
I think you might need to move on to the next question.
Okay. Sorry, Len. Carl, please ask your question.
Okay, hello, can you hear me?
Yep.
Yes, great. Okay. Regarding your test method, you said you used Mehra, but the A in Mehra stands for multiple stimulus with hidden reference and anchor. What anchor did you have in your testing?
So in the paper we stated it as a Mehra-like experiment. It's not exactly Mehra, exactly for this reason. The reason that we don't have officially anchor, because, for example, to put a monosignal as anchor or something other for comparing spatial sound is hard to decide what is a good anchor. But also by just using first order standard reproduction, it's already kind of can be kind of an anchor in this experiment. So if I can go back to this, yeah. So the first order here, this can be used as anchor, but yeah, we don't have an officially anchor here. Yeah, is this answering your question?
Hi, I also have a question. Thank you very much for your interesting talk. First of all, I think it was really interesting. Your work reminds me of some specialized way to record binaural sound somehow. I can imagine that it is nice for individualizing HRTFs, but did you do something like a comparison to an actual artificial head or something?
No, so here we used only artificial head. We haven't used actual personal HRTF in the experiment. So when the sound source was in the horizontal plane, and also in the experiment we didn't have head tracking. It's another limitation of the experiment. But still, the result is quite significant. So yeah. So we think that also with personal HRTF it will be similar.
Do you expect similar performance to an artificial head? So, with your method?
So this is with artificial head, the result that we see here. Both the objective result and the subjective result. Yeah. I see. I see what you mean. You mean directly measuring the binaural signals using dummy head. Yeah, so this is a good question. So there is a new paper. I forgot his name, but from Jens Aren's lab that performs quite comprehensive experiment comparing artificial head measurement to reproduction using a spherical microphone array. And they perform different methods, including the standard equalization method that we see here. And they concluded that they need order 7 and above in order to get similar results to artificial head recordings. And they showed that all the different equalization and processing types are achieving similar results. Also, the one that I stated here in the future work. Yeah, also they compared also this one, and they show similar performance with the standard reproduction. So, yeah. So I think I think that our method can perform good even compared to this. Yeah, we can reach out offline if you like to talk about it more.
Hey Samir, thanks for the nice talk. One more question. Could you elaborate a little more about the rotation, the head rotation, head tracking, how you would implement it?
Okay, so yeah, the question was
tricky.
Maybe to elaborate more about the head rotation. So yeah, so as I said, this is the limitation, and it's for future work. We didn't really trying to solve it yet, but there was a talk yesterday that presented. The title was something with a coherence something. They suggested to adding head rotations for binaural signals. So we can use such method to add head rotation here also, just by applying different ITD and ILDs according to the head tracking. But we also, yeah, we would like to investigate also different methods for this. Yeah.
Okay. Yeah, sounds tricky. Thanks.
Yeah.
All right. Len, do you want to try asking your question again? No, still can't hear you. Sorry, Len. One more? David, ask your question.
Hi, this is David. Thanks, Zamir, for the great talk. And just following up on Johannes' comment. Yeah, Johannes, I just wanted to suggest that if you have any idea, we agree that this is a tricky part, how to add head tracking to this approach. But knowing that you are working on similar techniques, if you have any idea, please reach out, and yeah, maybe we can collaborate on that.
Yeah, thanks, David. Yeah, so if anyone has any other question or want to discuss, we will be happy to meet in the lobby. Yeah. Thank you.
Yeah,
Thanks.
Peter, it turns out that the next paper
welcome Maximilian Kentgens. He's from my group at RWTH Aachen University. The talk will be in a similar context actually as the last one. It's on manipulation or modifying a recorded sound scene to improve or change it. Here it's interactivity, and the title of the talk is Translation of an HOA Sound Scene by Space Warping. I see, before we start, I see some unhappy smiles here. Don't know what's going on.
I think you're not amplified.
Yeah, Peter, could you go back on air, please? Check that one more time.
Ah. Now, am I audible now? That's
Yes.
better. Oh, it
All
seems
right,
it's
great.
okay.
Why don't you go ahead and do the introduction one more time? We're in good time.
Okay, so I practice only.
Yeah.
Let me introduce the next speaker, Maximilian Kentgens. He's from my group at RWTH Aachen University in Germany. The context of the talk is similar to the last one. We have a recorded sound scene and we want to change it, but we want to keep the sound scene intact. Here, however, it's not enhancement in terms of noise reduction, but we want to translate the sound scene for interactivity. The title of the talk is Translation of a Higher Order Ambisonic Sound Scene by Space Warping. So the stage is yours.
Thank you very much, Peter Jax. Hello everyone, and welcome to my talk. I'm very delighted to give this talk on translation of a higher order ambisonic sound scene by space warping today. I hope you can see my slides. A spherical microphone array is the one shown here on the slide. Allows to record spatial audio, and we can also capture information on the direction of incidence, which we here denote with inclination angle theta and an azimuth angle phi. And we encode the directional information in terms of higher order ambisonics coefficients, which we here denote as psi and m. So what was A in the previous talk is now our psi and m. And the ambisonics recording can be consumed then either with a multi-loudspeaker arrangement, or we can also use head adaptive binaural sound. And then the user is able to use all rotational 3 degrees of freedom to enjoy the music or the content. But however, for fully immersive user experience, it would be desirable to allow the user to move around in the scene. So this means that the user can approach sound sources so that they get amplified or attenuated, and also the direction change. And such a system can be called 6 degrees of freedom, or if the translation is limited to a region around the original position, 3 DOF plus. But since we do not have any information on the sound field at the translated position, we only have the original signal phi and m. We have to think of a clever solution to find a plausible estimate for phi tilde from the given signal phi. And we are not the first tackling this problem, and I think I cannot tell our story without giving some of the context. I think it is important to understand that there are basically two classes of approaches, which are shown here in the table. In the upper part of the table, with the yellow part, there are the phase correct approaches. You might call them sound field based approaches, since they usually aim for a physical correct reconstruction. And they're usually non-adaptive and robust. And they don't require source distance information, but they are limited in translations within the sweet spot. One special role here plays the very impressive work by Bernie et al., who used sparse constraints on the signal, and with the help of compressed sensing, they also achieve very good performance beyond the sweet spot. And the second category of approaches is very different. They usually use geometric approaches and are usually signal adaptive. And they don't care about phase information and other things. They are rather treated for good psychoacoustic performance. And these methods also allow to move out of the sweet spot. Of course, such methods may be prone to time-varying artifacts. And one thing to notice is they use a geometric model, so they usually require information on the source distances. So what we are going to present is a novel approach, which is a hybrid approach. It is non-adaptive and therefore inherently robust, but it is aimed to achieve good psychoacoustic performance, even for translations beyond the sweet spot. Before going into the details, we have to check the mathematics. And our sound field model is either a superposition of plane waves or a superposition of point sources. Here P is a sound field, and P is complex since it is the Fourier transform of the signals where the wave number k is proportional to frequency, and our generating functions for the plane waves is the exponential term, which is multiplied with the function psi from all directions as u, so that psi plane wave is the angular density of plane waves. And if we set this function to just a direct impulse from one direction, we would achieve the sound field shown on the top right. The superposition of point sources is similar, but instead of a plane wave term, we have a point source term consisting of a phase term B and an amplitude dka. And again, if we here set psi ps to a direct impulse from one direction, we would obtain the sound field shown at the bottom right. But it's very important to see now that there's a constant source distance S0 here in this model. And now, since psi ps and psi plane wave are simply functions on the sphere, we can simply describe them with a spherical harmonic series expansion, where y and m are the basis functions, and psi and m are the coefficients that describe our signal phi. But in practice, we have to cope with band limitation, a spatial band limitation, and we have to introduce a truncation order, which is n. And one note is that phi and m for the plane wave is nothing else than the higher order ambisonic signal that is probably known to many of you, and the psi and m point source is the near field compensated ambisonics. If we now introduce a truncation order, like for example in the plot here n equal to 6, this means that we only have a sweet spot of a limited size, and everything outside is disturbed somehow. So again, you can compare it to the last slide, the plots, and you see that there's now this green circle, which is the approximate region where the sound field is valid. And note that we're here considering normalized distances, so it's k times s, which means for a truncation order of n equal to 6, we would have 1.3 meter diameter of sweet spot at 500 hertz, but if we go to 5 kilohertz, it would be only 13 centimeters. And it's also very important to note that we simply can convert between psi plane wave and psi point source, at least in theory. And in the spherical harmonics domain, there's simply this conversion factor. Now, with our mathematical tools at hand, we can have a look on existing approaches, namely the plane wave and the point source translation method. So again, we want to find a translation operator which translates our signal psi and m to psi and m tilde, and we can simply achieve this if we consider our sound field model and replace the x by x plus d, where d is a displacement vector. And we obtain a p tilde. And if we do all the mathematics or the derivations, we arrive at the, for example, at the plane wave translation method that you see there. So there is simply a phase term, which is very interesting. So if we translate along a plane wave, nothing else than the phase changes. The amplitude doesn't change, the directions don't change, which is on the first glance not very intuitive. And when I considered this the first time, I was really wondering how this can work with near-field sources. But you will see that it can, but only for a very limited displacement. And there's the point source translation method, which is probably even equivalent to the plane wave translation method. I'm not entirely sure, but I think so. And I won't go into detail about this now, but one interesting fact is that the point source translation has some structural similarity with what I'm going to present now. So now you know the plane wave and point source translation methods. And now I'm going to introduce our novel approach, which is translation using space warping. So what is space warping? Space warping is quite intuitively to get. The idea of space warping is to modify the spatial arrangement of the sound scene by squeezing different regions on the sphere. This is what you see in the illustrations on the right. For example, if we move away from a stage, all musicians are squeezed. And if we approach the stage, the musicians have a larger angular span. So this is the basic idea. And the formula for the space warping is simply what you see here. We replace the angle theta by f, the inverse of f of theta tilde. So f is a warping function. And we only consider space warping along the inclination angle theta because we can simply rotate our ambisonic signal without any loss, and then we can only consider signals and warping along the z-axis. So warping function f is the first choice, and then there's in red, the equalization function. And the equalization function is some function that we can choose as we like. For example, if we choose it as shown here, we would preserve the energy after the operation. But we will see if this is useful for our application. Okay, so this is what I already said. The point source translation may be interpreted as a form of the space warping due to some structural similarity. If you want to know all the mathematics, I invite you to have a look in the paper. So now we have the space warping, and we plug in a geometry-based warping function. And this complex formula that you see here is nothing else than what you see on the top right plot. So imagine you're at the position of the blue dot, and you have sources in a constant source distance S0, which means the blue circle that you see there. And if you now move along the displacement vector d, then you arrive at the red dot, and the angle theta changes to theta tilde. And the formula that you see there is nothing else than the geometry, where we introduce the warping factor beta, which is the ratio between the displacement and the source distance, so that beta equal to 0 means we are not moving at all, and if beta is close to 1, we're very close to the sources. And now we have to discuss how to choose our equalization function. And we are basically considering 3 different flavors of it. First is the energy preserving variant, and the second variant now introduces an amplitude adjustment in addition to the energy preservation, according to the inverse square law of distance. So that if we approach a source, that the sources also get louder. So intuitively, we would say that energy preservation maybe is not that good, because if we approach a source, we assume that there's more energy in the signal. And the third flavor also, besides the amplitude adjustment, introduces phase term to correct for the phase, because the first 2 variants don't care about the phase. So now we have 3 equalization functions, and in our evaluation you will see how we will have some problems with the physical correct variant. And there we are already with the evaluation. And we're doing a simple experiment where we have two sources in a normalized distance with k times S0 equal to 17, which means that, again, this normalized, that at 500 Hertz, the sources would be in 1.8 meter distance, and at 5 kilohertz, it would be 18 centimeters. And these sources generate the sound field that you see on the bottom left. But of course, our algorithm doesn't know the whole sound field, but only a spherical harmonics expansion to a order n equal to 6, which you see in figure B. And what you see in the green circles is identical, almost identical, and outside there's a large error. Now we are considering two experiments. First, we want to translate to a position which is where the sweet spots are still overlapping with the original sweet spot. In the second experiment, we are moving further away so that the sweet spots are not overlapping anymore. And we are evaluating the performance with two different instrumental metrics. First of all, we have the similarity of angular distribution of power. So red, what you see in red is the output of our algorithm, and psi ref is the ground truth that we are comparing against. And we are comparing the distributions of the energy. So we build the inner product here. So that sigma equal to 0 means that they are very dissimilar, and 1 means we have an identical energy distribution. We're also considering the energy ratio, which is just comparing the energy of the output signal with the ground truth. And we want to achieve 0 dB, because if we have some attenuation or amplification, we would expect to yield heavy coloration in the signal. What we also plot here in the signals, in the following, are the localization vectors, which are basically a very simple summing localization model. The energy vector is the center of gravity for the energy distribution, and the velocity vector is the center of gravity for the amplitudes. Okay, what you see here is the reference signal on the top right, and you can compare it to the plane wave translation and the point source translation method. And the first thing that you notice is that the plane wave and the point source translation method look very similar, with the similar outputs. The second thing to notice is that if you have a closer look to the region within the green circle, you see that the left half, which is overlapping with the original sweet spot, looks very similar to the reference. But the right half in the sweet spot is different. And this yields a mixed performance in the spatial fidelity metric sigma, which is only 0.46. And I would say that the energy ratio is okay with minus 2.3 dB. So how does our novel approach compare with this? Have a look on the bottom left. This is the warping variant with phase correct equalization. And if you have a look on the sound field themselves, they look very similar to the plane wave translation, the point source translation, especially in the left half of the sweet spot. But the spatial fidelity metric sigma is a bit better, and with a similar energy ratio psi. A similar performance is achieved with the energy preserving warping variant. But now, if we have a look on the amplitude adjusted variant, you see that there's even an improvement with this in sigma and in psi. But I think even more interesting is the case when we have translation or displacements out of the sweet spot. And this is what you see here in the second experiment. And you see that all phase-correct variants totally fail, both in spatial similarity and the energy ratio. They all score very bad. But the proposed methods, the warping with energy preservation, and especially the warping with amplitude adjustment, score very high. Especially the amplitude adjustment has very good results here in this example, even for the energy ratio. Because we are on AVAR, on this conference where we have the possibility to really listen into binaural signals. I prepared something. It's rather a toy example, even a bit quick and dirty. I'm sorry for this. So we have two sources. It's pop music and a male speaker from two different directions. We have the recording from at the blue cross. It's the input signal. And we have the reference at the red cross. And then we listen to the plane wave translation method, the warping with energy preservation, and the second flavor, the amplitude adjusted variant. So normally, I was really impressed when I listened to these signals in our lab with loudspeakers. When I moved around a bit, I'm a bit disappointed about the binaural rendering, which is really bad. But I hope that you still get the idea. I'm sorry for this. And one thing to say also is that I'm now playing all the 5, and then I repeat the reference and again the warping variants, so that you can hear the items twice.
The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or... The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or... The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or... The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or... The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or... The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or... The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or... The lobes of her ears were pierced to gold rings. A white silk jacket goes with any shoes, either mud or...
Okay, if you're interested, I can also send you the raw ambisonic signals, then you can have create a better binaural rendering if you like to. Just contact me if you're interested. And this already was our small glimpse into our work. But before concluding, I also want to thank our reviewers for their very fruitful comments, which helped us a lot with this work and which will also find application in our future research. So we presented a novel approach for translation of scene-based, so really recorded ambisonics based on space warping, where the idea is to squeeze and stretch the angular source distribution according to a geometric model. And we found that correct phase adjustment is potentially even detrimental, which is very, very interesting, I think. And with our psychoacoustically motivated very simple metrics, we achieved superior performance, even for translations beyond the sweet spot. And we see VR and AR systems, immersive teleconferencing and telepresence as possible applications for our work. Thank you.
Okay, thanks, Maximilian, for the nice talk and the great overview. There's time for questions. We have roughly 5 minutes, so the floor is open for questions. Raise your virtual hand if you have any questions.
I have a
Chris,
question.
please ask your question.
Hello, Chris Travis. Thank you very much. That was very interesting. My question first question about the phase realization. Did you try it with different test materials, including highly transient materials where time aspects of rendering might be more critical?
No, we did not do this. I think our work is rather theoretic. If you have a look on the paper, we are considering single frequency cases, and we didn't put a focus yet on the evaluation, and this is really subject to future research. I would also be very interested to see how performance is with more complex acoustic scenes. But I think I'm very hopeful that we will achieve good performance for many cases, practical cases. Hope this answered your question.
Next question. Boaz, ask your question.
Yes, thanks very much for this nice talk. So I have a question about the distance of the source. Do you assume that you have this distance, KR equals 17, I think it was, and then the reference method, I think, doesn't have that distance. So is that correct, and how is it sort of treated?
Yeah, I think this is the most important point, that you have to need this additional information. I don't know, dependent on the scenario, there might be, you might know this beforehand, you could make some estimation on the source distance, but you need this information. Maybe it's not so much of a problem if the distance is not very correct in terms of psychoacoustic plausibility, if you use some degrees offset. But all these geometry-based methods need information on the source distance. And you could also merge.
Thank you.
You could also imagine cases where you don't have a constant source distance, but maybe a function dependent on the angle or something.
Yeah, thanks.
Welcome.
Remy, please ask your question.
Okay, thank you. Yeah, thanks for the talk. I had a couple of questions. The first one is, maybe you've touched on that, but how big of an area do you expect this type of method to work for? Are we talking about walking around maybe within a meter kind of radius, or potentially more? Yeah, I guess that's the first question.
So maybe some motivation is that we recorded an orchestra with an eigenmic and put the eigenmic in the middle of the orchestra, just in front of the conductor, and everyone. We also had video with this, along with this, and everyone also wanted to approach the violas and all the instruments, and so it's rather intended for 3D or F+, so moving around close to the original position. To making yeah.
And then I guess my other question is, I know there are people who there's this approach where you interpolate between multiple ambisonic chapters. I was wondering if you've considered combining your approach with having multiple microphone feeds potentially that you could analyze to get better accuracy, for the translation.
This would be really interesting. For example, if you have multiple arrays, you could also solve the distance problem. But we are not considering this. The advantage of our method is that we can simply work on existing ambisonic signal, and
Right.
I think there's a lot of work on multiple SMA interpolation, but we're not planning on considering this at the moment, at least.
Okay, thank you.
Good. So many thanks. Let's thank Maximilian Kentgens again. And also thanks to the question, for the questions.
Thank you.
Good. So let's switch to the next talk. I see Christoph Perschmann already here. Okay, I see here the slides are up.
Yeah, let's just try to proceed, and then if the other rooms can't see it, we can get some feedback.
Okay, if you are ready, Christoph Perschmann.
Yeah, we just to get access to the laser pointer.
Yeah.
I think I got it, and yeah. All right.
Good,
So yeah.
Shall I introduce you briefly? So
Yeah,
let me
of
introduce
course.
the next talk then. Next talk is given by Christoph Perschmann. He's from TH Köln, Technische Hochschule in Köln in Germany. Well, the talk will be on a comparison of spherical harmonics and nearest neighbor-based interpolation of head-related transfer functions. So again, a nice combination, I think, of HRTF technology and spherical harmonics. The stage is yours.
Yeah, thank you very much for the kind introduction. As already said, the topic I will talk on today is on interpolation of HRTFs. And I think you all know and you all can imagine that this is not really a new topic. And I already can promise you at the very beginning, most of the stuff that I will present is maybe 20, 25, or maybe up to 30 years old. So it's not really completely new. Now I see some unhappy faces. Is there anything not correct or anything? Moment.
Christoph, can you check that you're on air? Sorry, I should have asked this. On your host tools.
Yeah, I will. Oh, I lose a. I'm on air. Yes, I am. Amplify my voice is set, and microphone amp is set, and maybe I try to increase any kind of loudness. Is it better now? You can hear me?
Okay.
Yeah? It's getting better, yeah?
Yep, looks better.
Looks better, all right.
Yep.
Then I try to get access to my laser pointer again, which I somehow lost, but it is something that might happen in the end. Yeah, no, I don't have any longer a laser pointer. Okay, so it's about interpolation of HRTF, and as I already said, it's not really a new topic, which I am talking on today. And you will see in a minute that many of the studies, well, are from the 90s and beginning of the 2000s, which I relate to. I do not have really to describe you that measurement of HRTFs are important if you're talking on headphone-based VAEs. That we would like to access these HRTFs on spherical sampling grids, and that in many cases we have measured the HRTFs on a sparse sampling grid, and thus there is need for some kind of spatial interpolation or for some kind of upsampling. Yes. Again, amplify my voice. Better now?
Much better.
Am I audible now? Yeah,
yes.
Okay. All right. Looking back to the previous two early studies on interpolation, there are lots of methods available, and I do not want to do just another study and to increase the mass on different interpolation techniques and comparisons and all that stuff. The idea of this study was to bring together completely different ways of doing interpolation, because there are completely different approaches. If you look in very early time in the 90s, there mainly were done nearest neighbor-based approaches. So you can refer to Wenzel and Foster, 93, so 27 years ago, or to Hartung or so on, who applied nearest neighbors and then did interpolation, spatial upsampling by HRTFs. Then Spherical-Harmonics seems to be very new and modern, and we hear it quite often on this conference and other conferences, but it is as well from the 90s. So it's a very nice paper from Evans et al., who did interpolation, spatial upsampling there, and nearly everything was there. But he did, for example, not do comparison to nearest neighbor-based approaches. And then if you refer to a paper from Langendijk and Bronkhorst, there's a study who did not do the interpolation based on the complex spectrum, but separately for magnitude unwrapped phase. And they had very good results. And there was one of the big things in 2000 where we said, well, it's really great how you can interpolate HRTFs. And then pre-processing of HRTFs before doing interpolation is now a hot topic. So there was a paper from Zamir on ear alignment, and we did a study as well as published in the IEEE paper on with the so-called subTQ method. Lots of method doing pre-processing. But if you have a little bit more look in detail, you can go back to the 90s, look at this study from Hartung or another paper from Jelani et al. 2000. Nothing is new. And so I would like to compare these methods because there are really no comparisons around, for example, combining nearest neighbor-based approaches with specific pre-processing methods and maybe do the interpolation separately for magnitude and phase. So the idea is to bring together and get an idea what works and maybe what is not beneficial combining, or what should not be combined, and maybe which interpolation technique works best, or it doesn't matter in the end. We will see. At the very beginning, some description, or maybe to give you some idea what the difference is between doing the interpolation of the complex spectrum and on magnitude and phase separately. So I have very simple sketch of two HRRs, and we maybe for different directions, and only the left ear is shown. And we would like to interpolate to a direction exactly in the middle between them. And you all would agree that this should look something like that. The amplitude is averaged, and the initial time delay which we have is somehow averaged as well. But if we do the interpolation on the complex spectrum, it doesn't depend, by the way, not if it's on the time domain or a complex spectrum in the frequency domain, we get something like that. Two peaks, none of them in the right position, and yeah, just somehow with some amplitudes, and you all can imagine that with that will give spectral distortions and all the things we are talking on here when we look at artifacts doing interpolation. It's no wonder, not a big surprise. If we do the interpolation separately for magnitude and phase, so we do phase unwrapping and interpolate the magnitude and the phase, we get this purple curve. And this, in this simple example, matches exactly the reference. So the amplitude is averaged and the phase, and we get something like that. So that seems to be fine, and that should might give you some idea why the concept of splitting up the complex spectrum in magnitude and phase might be beneficial, might help. Another thing, what we could do is doing some pre-processing. And typically the pre-processing in the end, and it doesn't matter if it's ear alignment from Zamir, our subTQ or older methods, they're somehow based on the idea that we would time align the HRIRs. So in an ideal case like that, yeah, in some pre-processing. And if we then do the interpolation, it doesn't matter if it's complex spectrum or if it's magnitude phase, it's all the same, and it all results in, oh, there's some delay in the slides, I see. It all results in the same thing. So we see, yeah, it seems to be optimal, seem to work. There are lots of pre-processing approaches around. So there's the idea that in the 90s, they had the idea of cutting the initial delays of the HRRs, maybe on subsample basis, and then doing interpolation. And of course, oh, I forgot that, after the interpolation, you have somehow to invert this pre-processing and to put everything in the right position again. Of course, that's important. Newer modern methods, so this substitute method from our lab and the ear alignment from Zamir, Ben-Hur and et al., which is from basic idea very similar, very much the same, had the idea to apply some kind of spherical head model and to do some equalization, and this results, you can imagine, in some time alignment of the HRR, if you look at that in more detail. There's a very nice paper comparing pre-processing methods, which had been presented at exactly that conference here 2 years ago from Fabian Brinkmann, 2018. Substitute and ear alignment is missing. They have been invented later, but yeah, you can refer to these pre-processing methods, which is quite worthwhile reading. So I would like to bring the interpolation in some kind of block diagram, and what you see now is nearly trivial. You'll see sparse HRTF set sampled on the sparse sampling grid. Surprise, surprise. Then we are doing some kind of interpolation, and we end up with a dense HRTF set on a dense sampling grid. I think you will agree that this is the idea of spatial upsampling. But the important thing is that in this block of interpolation, there could be everything put in. We can put in SH-based, Spherical-Harmonics-based interpolation methods, or we can put in nearest neighbor-based interpolation methods, or if you invent a new interpolation method, you can apply this there. And the other thing we look at is the data representation. So on what data are we doing the interpolation? On the complex spectrum and the magnitude unwrapped phase separated? That's what we are doing in the study, or maybe you're doing it on something totally different, on some I don't know, on some other components that you can make up of principal components. You can interpolate them as well if you want. So what we fill, and in which way we fill this interpolation block is up to you and can be varied. And you can imagine that we as well can combine different interpolation methods with different forms of the data representation on which we do the interpolation. Our block diagram is getting a little bit more complicated, a little bit more advanced if we add the pre-processing. And I added the blocks in this block diagram in the way as we did it from the concept in the substitute, in this spatial upsampling method that we invented. So the idea is we start with a sparse HRTF set, which you can see on the left, and we have some kind of equalization data set. So this is a spherical head model, and what is called here equalization is the same as described before as doing the time alignment. This is a result of this equalization. So we have equalized sparse HRTF set, and in this diagram I shifted the ears to the center, so it's as well comparable to what Zamir presented about 1 hour ago with his ear alignment. So somehow we were also shifting the ears to the center, and this reduces the spatial complexity, or with other words, it somehow does time alignment of the HRRs. It's the same, just with different words. Then we do the interpolation as already described. We end up with a dense HRTF set, and we invert this equalization. We invert the pre-processing, and in our way we are doing the substitute method. We apply again the same data set, equalization data set, a spherical head model. Okay. So how can we combine this? And I would like to show you some of the results. So what we did in our study was not a perceptual study. We did some technical evaluation, but you will see in a minute that all the technical measures, all what we determined, point in the same direction. So we get a good idea what we can combine and what not. So we used dummy head recording, the Neumann KU100 measurements, because they were carried out on a dense grid with 2,702 directions on a Lebedev grid, and we did SH transforming to an order of 35. And from this data, we created some downsampled, spatially downsampled data sets, so our test data sets with 14, 38, 86, 170 directions, and this corresponds to orders of 2, 4, 7, and 10 if we are thinking in the SH domain. And then we did the interpolation, either spherical harmonic based, just spherical harmonic, no regularization, no Tikhonov, nothing specific, just the basic thing. So there's room for more, of course. And on the other hand, we applied a nearest neighbor based interpolation. And we did some pretests and found that it is only small differences between what nearest neighbor based method we choose, and then we choose in the end natural neighbor based natural neighbors as a method with a barycentric approach, and as nearest neighbor based. And the same we did for the pre-processing. So we just chose one representative. We chose the method that we invented, the substitute method, but we could have done it the same with ear alignment or something else. And as an example, pre-processing method and combine all this stuff. So we created test data sets at this for these 4 spatial grids with some either with some combinations. So Spherical-Harmonics or natural neighbor-based interpolation methods, indicated by the abbreviations SH or NAT for natural. And the data representation, either on the complex spectrum or separate for magnitude phase, and magnitude phase indicated as abbreviated by PH. And we did exactly the same for the preprocessed data set, substitute preprocessed data set, and we indicated that by the abbreviation DEQ. So we have 8 different kinds of test data sets at 4 orders, and it would be great if you could have an idea on remember these abbreviations for the next 10 minutes, because we show them on the next plots and so on. So the first thing we looked at were the magnitude of the HRTFs. And we started very simple with just one example direction, 45 degrees from the left. We're just looking at the left ear. And the sparse grid, the starting grid, was a elaborative grid with 38 sampling positions. And yeah, no pre-processing here. The reference, exact reference, is looking like that. And if we then are doing interpolation in the SH domain, we get this. Well, the errors start already at 2.5, 3 kilohertz, and well, it doesn't look so fine. If we do natural interpolation, it's not better. So it's in that case worse, maybe for a slightly other direction, it's vice versa, but both doesn't work fine. But if we do the interpolation separately for magnitude and phase, and maybe you have in mind one of the sketches from the beginning, what the idea behind that is, we get something like that. Both curves match the reference much better, so it seems to be quite okay. So we see that this interpolation separately for magnitude phase seems to work fine, seems to help. On the next plot, on the next slide, I show the same thing for the preprocessed data sets. So again, the reference, SH-based interpolation with preprocessing, well, looks much better than before. Natural interpolation with preprocessing, about the same, no big difference. And this is the same, separate from magnitude and phase. All curves look the same. So in the end, it seems to be, if we do the substitute preprocessing, it doesn't matter if you're doing natural interpolation, so nearest neighbor-based interpolation, SH-based interpolation, and it does not matter as well if we do this for magnitude and phase separately or complex spectrum, because this preprocessing shifts, you remember the second sketch, which I showed, shifts the timer lines, the HRRs, and that works fine. And if you got that information, that's nearly all which we need for the take-home message. I just go through different other measures, of course, now not only one single direction, but we will always see the same. We continue with ITDs. Reference here and no preprocessing, and again it bases on the elaborative grid with the upsampling basis on the elaborative grid with 38 positions. And if we do interpolation SH-based, natural interpolation based without preprocessing and on the complex spectra, looks like that, not too good. If we do the interpolation separately for magnitude and phase, you can see it on the blue and on the purple curve. The results get much better and yeah, much closer to the reference. And so again, interpolation separate for magnitude phase seems to be an increase. The same for the substitute preprocessed data sets. SH-based interpolation, natural interpolation, natural SH-based interpolation separate for magnitude phase in blue, and natural interpolation. So in the frontal hemisphere, or the frontal part direction, they look all the same. There are differences which are below the J&Ds. We described in some more detail in the paper. To the sides, there are some differences. In this case, we can see that the separate interpolation of magnitude and phase does not give an increase in that specific case. It might be a little different for other measures. And then the ILDs. And the trend is always the same. It's bad if you're doing the interpolation separately, not separately for magnitude phase, but if you do it SH-based or natural-based without preprocessing, And on the complex spectra, it's getting much better if we're doing it separately for magnitude and phase, as you can see here. And if we apply the substitute preprocessing, we can nearly in all cases be happy. It looks much better. What we can see here for lateral sound incidence, there seems to be some specific things for the SH-based processing. This might depend on the specific Lebedev grid. It might disappear or change if we use a Fliege grid or another grid. So there are some specifica which we did not include in that study, which might be worthwhile looking at. Yeah, but it's just specific detail for lateral sound incidence. In the next step, we look at some spectral differences over frequency. So x-axis is the frequency, y-axis is the spectral differences, and it's averaged over all sound incidence directions. So we create sound incidence on a very dense grid, based on on sparse grids, with 14, 38, 86, 170 directions, and they are plotted with the four different colors or different variants of red here. And you see that is a steep increase for the SH-based interpolation, which we can see here at some frequency which depends on the order, and that is exactly what we see. It's the spatial aliasing frequency, where it starts or where it gets large, and it's this effect of spatial aliasing, what we can see here. If we apply the substitute preprocessing, everything is getting much better. We do not have this strong increase here, and again, we could apply another preprocessing method. It would be basically very, very similar. That was a basic idea of this substitute method and one of the basic plots we showed in that paper there. But if we do it with natural interpolation, we get that error, so we get as well, depending on the size of the grid, these increasing errors. And if we do apply the substitute processing, it's getting much better. So, and if you compare the blue curve from that slide and maybe from the previous slide, maybe that works, you can see, well, they do not seem to be too much different. So in the end, if we apply the preprocessing, it doesn't matter if it's natural interpolation or it's H-based interpolation. If we do the interpolation separately for magnitude and phase, you can see the red curves here. So without preprocessing, they're already much better. And we do not see a strong increase, so it's not getting better. The errors are not getting smaller if we apply the preprocessing. And next slide nearly shows the same for natural interpolation. Well, if you look at that, it's nearly all the same. The funny thing from our point of view is the best curves, so either separate for magnitude and phase, or if you apply preprocessing, they all end up in the very, very same range. So there's not a big difference there in the end. So it seems to be some kind of, I don't know if it's a limit, maybe that's the information we can get out of that with the interpolation, the information that we have. We always end up in a very, very similar range. Finally, there's just one more measure which I want to show. And again, the trend is always the same. Again, spectral differences, but now we look at the distribution over the direction. So they are average in frequency, for frequencies up to 10 kilohertz, linear averaged, and you can see on the x-axis of each of the plots the azimuth, and on the y-axis the elevation. Zero elevation is horizontal, and 90 is top and minus 90 at the bottom. And you can see in color the errors, deviations. We can see in each of the plots, I don't have the laser pointer, so I cannot really show, in each of the 4 plots on the left side, you see the errors at the contralateral ear, which are quite large. So we have the largest errors at the contralateral ear. Not a big surprise, it's a common thing that we see. And it's a little better on the ipsilateral side, so on the right side of each of the 4 plots that we can see here. And in the top row, you see the diagrams, the plots without preprocessing, and in the bottom row you can see the influence of the preprocessing. We see it's getting much better. The errors, especially on the ipsilateral side and on the frontal direction, are getting much, much smaller. And the left and the right part of the 2 plots, one is SH and the other one is natural interpolation. So we can see again, if we are doing solely SH interpolation or solely natural interpolation without preprocessing, we have large errors and they are reduced by the preprocessing. If you do the same interpolation separated for magnitude and phase, then it's getting more and more boring because nearly all the plots look the same. Yeah, we have nearly all the same quality. The errors are not exactly the same, but they seem to be very, very similar. We are good at the ipsilateral side and pretty much worse on the contralateral side, a little bit worse on the contralateral side. And if you compare to the previous slide, to the bottom row for the equalized for the preprocessed data set, and that one here, you see, well, there is not much of a difference. That brings me nearly to the end of my talk. Now is the thing that makes me most nervous, because I have no idea if the listening sample really works here. This is a critical thing. So you will hear all the different data sets from a direction from 45 degrees from the left. The interpolation basis again on the data sets with the 38, the sparse grid with 38 directions. And you will always hear first the reference stimulus and then the test stimulus. So the difference between these stimuli gives you some idea of how good the interpolation is. And you will always see in red indicated what actually is played.
Krista, can you advance the slide?
Yeah, maybe in my version it's still running, but yeah.
Ah, okay. I thought it was.
But I just heard a delayed version of that, as we know, and yeah. Okay, so I'm not sure if it worked for you or not. I did not get to see many responses there. I wasn't pretty sure. Typically, you might have heard, so if it worked, that only the SH-based interpolation, the network interpolation, worked, where they had significant differences. And all the other interpolation methods, there was not much of a difference. Of course, audible difference to some extent, but they are pretty small. And if we have not done a formal listen experiment, but if we did so, I guess the differences would not be too large in the perceptual differences. So what are the next steps? We could, for all of these methods, do much more. For example, if we analyze the SH interpolation, we could apply Tikhonov regularization, do much more things, all the stuff which has been done in lots of studies and incorporated in our study. So we just kept it simple. We could look at robustness to measurement inaccuracies. It's a very interesting thing. And if you're heading towards individual measurements, you should take care on that. We could compare different nearest neighbor-based approaches. We could analyze different preprocessing methods. And of course, we could do a track acoustic evaluation. But that was not the scope of that study, but the idea was to keep it as simple as possible to give you an overview of the different methods. And I hope that you get some idea on that. So what you please should avoid is doing the interpolation of the complex spectra. And it doesn't matter if it's nearest neighbor based or if it's SH based. If you do this without preprocessing and not do the interpolation on magnitude phase or on other issue, maybe process things, it doesn't really work fine. If you don't want to do preprocessing, you can do interpolate separately magnitude phase, or you apply preprocessing. Furthermore, we found that the combination of doing this separate magnitude phase interpolation and preprocessing does not give a big benefit. It helps to some extent, but you should not expect too much of that. And well, I did not explain that in so much detail in the slide and the presentation here, but we got in the end the best results. It was funny for the nearest neighbor-based approach and separate from magnitude phase. And that brings me to the very beginning of our story, because this is something that has been invented in the 2000s. So Langendijk and Bronca's paper, they described something like that. Yeah. So the interesting thing for us was we can do very, very nice, implement nice ways of interpolation, but we should look back to studies from former times 20 years ago, because maybe with totally different methods, they achieved very, very similar results. And that was really fun, interesting looking at that methods from the 90s, from the early 2000s, nearly performed similar than our newest and advanced methods in HRTF interpolation that we have. Thanks for listening.
Good. Thanks for the great and interesting talk. I think we have maybe time for one or two brief questions. I see two questions, I think.
Hey, Jacob, please ask your question.
Okay.
Yeah.
Can you hear me?
Yeah.
Thank you. I was wondering, this interpolation, have you looked into any artifacts when doing dynamic interpolation, which is changing the angle between the interpolations, or is it just for static interpolation?
Well, not in this study, but we applied the method in informal tests, listening tests to non-static, so head-tracked method, or we had head-tracked listening samples, and no, we did not perceive specific artifacts for some specific methods. Maybe for the phase unwrapping, we have to take care that to lower frequencies, this phase unwrapping works fine, so we should have a look there. But no, we did not perceive artifacts for specific methods. It didn't, and as well not in dynamic scenarios. No, that worked fine.
Thank you.
And last question, Chris.
Mm-hmm.
Chris Travis.
Hi, thanks. Fascinating stuff. You chose one pre-processing method to apply your study, to create graphs for, but I'm sure you have a view on the relative merits of the different pre-processing methods. Could you comment on that also? Have any of the pre-processing methods zoomed in on sum and difference techniques, where one looks at the deltas between the two ear HRTFs?
Yeah, if we so we did not include in the study because it was a quite not a small study, but we would like to keep it somehow straight. But we compared, for example, some measures of the ear alignment of our sub-DQ method, so from Zamir Ben-Hur our method, and it's very much the same. And we did not formally test this method of cutting initial delays, but if you look at some older studies, this Jelani study that was 20 years ago that I was involved. I'm an old guy in that field, and I think it's in the end it's very much the same. We did lots of studies with our method and looked at just shifting the time and not looking at amplitude shifts and so on. I do not expect much of a difference in the end. Yeah, so. Of course, you need to take care, for example, if you're cutting initial delays and doing just some time alignment, that you do it on subsample basis maybe, and how to get this, if you're cutting initial delays, how you interpolate the delays and so on. So there are some things you have to care on, but if you do this appropriately, I expect very much the same in the end. Very similar results. Not exactly, so if you go in details for specific directions, for example, contralateral sides and so on, there might be some things happening and you might tell me I have found something where there are differences, of course, but we saw it, for example, for ITDs, ILDs, but generally from a view far away, it's very much the same. Surprisingly for us.
Good. I think Yeah, I think we're running out of time. So although I see questions, but maybe there's an opportunity later in the lobby or in the coffee break to discuss in the space individually. Okay, we are 5 minutes after our scheduled time, but I think that's pretty good. Thanks to all the presenters. Thanks for asking questions, and also thanks for the staff in the background who did a great job in mitigating problems. And well, let's thank, I forgot that, sorry, Christoph Perschmann again. And then I would like to conclude the session and wish you a good coffee break and further great sessions in the conference.